Let's talk about dimension and rank. So first, the definition. If I have a non-zero subspace H, then the dimension of H, denoted dim H, it's just the number of vectors in any basis for H. And so notice this definition has buried within it a theoretical fact that we need to prove, namely the number of vectors in any basis for a space H doesn't depend on the choice of basis, right? So if you go and compute a basis and I go and compute a basis, the basis we compute might be different, but the number of vectors in them should be the same. And in fact, it is. The dimension of the zero space is by definition just going to be defined to be zero. So you may have some intuitive notion of what dimension means for more complicated objects, like curves, planes, or cubes, or balls, or things like this. But we're not going to talk about those in this class. And the reason is the definition is much more complicated. So remember, I like to talk about simple things, and so we're only going to talk about dimension for subspaces. So a related notion, if I'm talking about a matrix, the rank of a matrix, denoted rank A, this is the dimension of the column space of that matrix. Very similar to that notion is the rank of a linear transformation T. So this is denoted rank T, and it's the dimension of the image of T. So notice, we've already seen that the pivot columns of a matrix A form a basis for the column space. And since the dimension of the column space only depends on the number of elements in that basis, we see that the rank of the matrix is equal to the number of pivots of the matrix. You also see that if T of x is A times x, so T is a linear transformation with standard matrix A, then rank T is equal to rank A. And so this is equal to the number of pivots of A. And so we see it's row reduction to win again, right? So row reduction allows us to compute these dimensions. If I give you a collection of vectors in Rn, v1 up to vp, and let h denote the span of those vectors, then I can describe H as the column space of the matrix I get when I stack those vectors together. So A is v1 up to vp. So then the dimension of H is just equal to the rank of A, which again we can compute by row reduction. It'll be the number of pivots in this matrix A. So let's look at some examples. Suppose H is the span of these four vectors, 3, 2, 3, minus 6, minus 4, minus 6, 9, 7, 6, 0, 2, minus 6. Let's compute the dimension of H. So I'm going to write down the matrix I get when I stack those vectors together. And I get this 3 by 4 matrix, and I'm going to have to row reduce it. Now, I don't need to row reduce it all the way to reduced echelon form, because all I care about is the number of pivots. So you should pause this video and go and row reduce this for extra practice, and then you can come back and check. Okay, so if I did my arithmetic correctly, if you row reduce this matrix, you get the following echelon form. So I put boxes around my pivots to highlight them, and we see that there's 2 pivots in the matrix, and so the dimension of H is 2. Let's look at a more complicated example. Let's compute the rank of the matrix A, where A is this 4 by 5 matrix. So the first row is 1, 4, 8, minus 3, minus 7, minus 1, 2, 7, 3, 4, minus 2, 2, 9, 5, 5, 3, 6, 9, minus 5, minus 2. So if I'm computing the rank of the matrix, then I just need to row reduce to see how many pivots there are and count the number of pivots. So for extra practice, if you need extra practice in your row reduction, you should pause the video, row reduce, and then come back and check. Okay, so if I did my arithmetic correctly, the echelon form here, what I get is this matrix here. Let me put boxes around my pivots, and I see that there's 3 pivots, and so the rank of the matrix is 3.